All right, let's talk about formal charge. Now, it's possible to draw more than one Lewis structure in many cases where the octet rule is obeyed for all the atoms. So how do you determine which structure is the most reasonable? We're going to use the formal charge. As you move on to organic chemistry, formal charge is a little bit more of a big deal. Formal charge is a charge that would have if all the atoms had the same electronegativity, which they don't, but we'll just work with it. To calculate the formal charge, all the non-bonding electrons are assigned to the atom on which they're found. Half of the bonding electrons are assigned to the atom in each bond. So the formal charge is equal to the valence electrons minus half the bonding electrons minus all the non-bonding electrons. And the most stable structure has the smallest formal charge on each atom and the most negative formal charge on the more electronegative atoms. So what we'll do is we'll calculate the formal charge on each atom and each of the following. And we'll do cyanide, and then we'll revisit our friend CO2 that we did in the last presentation. If you haven't watched the basic Lewis structure presentation, go back and watch that first, and you'll understand what we're talking about. So if we look at our friend cyanide, we got carbon, we got nitrogen, so 1 times 4, because we got 4 valence electrons because in group 4A. So that's 4 electrons from carbon, 1 nitrogen times 5, because nitrogen 5A. That's going to be 9. Now we got a minus 1 charge. We're going to add 1, and that's going to bring us to 10. Now, if we draw our structure for cyanide, that's going to take away 2. It's going to leave me with 8. That's going to need 6. That's going to need 6, 12. And it can be very much like the case of nitrogen, where we're going to need a triple bond. And then we have to add electrons here and here. That whole structure carries a negative 1 charge. So what do we do with the formal charges then? The formal charge on the carbon is going to be equal to the number of valence electrons, 4, minus half of the bonded electrons. So how many electrons are got in triple bond? 2, 4, 6. So half of that is 3. Or just count the number of bond lines. Minus 3 minus the number of electrons in non-bonding pairs. So that's 2. 1 electron for each dot. And so that'll end up with a minus 1 formal charge on the carbon. The formal charge on the nitrogen will be pretty much the same calculation because you got the same bond, same non-bonding pairs, but you start with 5 electrons instead of 4. And so you get a 0 formal charge on the nitrogen. Now notice if you just count bonds, I told you in a previous the Lewis structure presentation, carbon like to have 4 bonds, but in this case it's only got 3 and it's carrying a negative 1 formal charge. So if you got 1 fewer bonds, negative 1 formal charge. Equal number of bonds, nitrogen likes to form 3, 0 formal charge. So you can get away in many cases by just counting the bonds and estimating the formal charge. A good way to check your work is that these formal charges have to be the charge on the compound, which they do. So alternately, now if we redraw our cyanide, instead of drawing the bracket notation, that cyanide is carrying the negative 1 formal charge. So a lot of times you'll draw the charge with a circle around it, and that indicates the formal charge of the atoms. And you can use that. Now, if we revisit in B, we're just going to revisit our friend CO2. And if you look at the previous presentation, we found that the proper structure for CO2 looked like this. But we said that this structure technically obeyed the octet rule. So let's look at each of those individually, and we'll see why this structure is better and that one not so much. Carbon is going to be 4 valence electrons. You got 4 electrons and bonds, no non-bonding pairs, so that formal charge is 0. Formal charge on each oxygen. The oxygens have the same number of bonds and non-bonding pairs. You have to count it into the addition twice if you got 2 oxygens, but you only really have to calculate it once. It's going to be 6. 2 electrons in a bond, 4 electrons in non-bonding pairs for a total of 0. But notice I considered here, sometimes you got more than one. Everybody wants to add up all the electrons from all the oxygen. No, just each oxygen has to be considered individually. So there's 2 of those, but it still adds up to be 0. So 0 formal charge and everything is stable. Now if I consider that on the other structure, you got 4 minus, still 4 minus 0. So that works out the same, but now the oxygens are different. We'll call this oxygen 1. We'll call this oxygen 2. So the formal charge on oxygen 1 is going to be 6 minus 3 for the bonds, minus 2 for the non-bonding pairs, but it's going to be a positive 1. Formal charge for oxygen 2 will be 6 minus 1 for the bond. Oops, we need some more electrons on that, don't we? Minus 6 for the non-bonding electrons, and that gives us negative 1. Still adds up to 0, but now this is carrying, the one with the triple bond is carrying a positive formal charge, and this is carrying a negative formal charge. And now that molecule looks polar. And that's not the experimental experience. So we'd say, nah, not so much to that one. And yay, that one works, even though they both obey the octet rule. Now, sometimes you don't get a good representation from a Lewis structure. Now, our friend carbon dioxide, we could use to decide which structure was likely. In the case of nitrate, as we mentioned in the Lewis structure presentation, you could draw more than one equally correct Lewis structure for nitrate. And so that's not quite the same thing. So we use double-headed arrows to indicate the resonance formulas. And so we want to draw all the possible resonance structures for nitrate. So this was the structure of nitrate that we had from the previous presentation, indicating those are resonance structures. They're separated by arrows. Any of those 3 structures would be equally correct. And so they form resonance structures that are equally likely. As you get into more advanced structures, then they may or may not be equally correct. It might not be one's right and one's completely wrong, like carbon dioxide was, but you may get one that's more likely than the other as you get to more advanced work. Now, another example, particularly once you get towards organic chemistry, is benzene. Benzene has got a 6-member ring of carbon, each bonded to 1 and only 1 hydrogen. You have alternating double bonds, but you got 2 different ways you can draw that structure. And so, some other molecules could include carbonate, sulfur trioxide, and ozone. But for the benzene, you've got some play because I can alternate where those double bonds are and draw them in the opposite places. Another way of looking at it would be to draw a hexagon representing that 6-member ring and then draw a circle indicating the resonance of the ring. That is, really it's not an alternating single and double bond. Those electrons are shared throughout the ring structure. And that's one way that Lewis structures don't accurately predict structure of the actual molecule and sometimes. So really it's more like every bond's a bond and a half and not a single and a double.